Assalamu alaikum rahmatullahi ta'ala wa barakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, welcome to this video about computational fluid dynamics again, CFD. In this video, we're gonna simulate or talk about simulations about the flapping airfoil, the variable pitch, or how to change the angle of attack while the simulation is running, and the variable pitch turbine, vertical axis wind turbine. It is the idea of VERTOGEN company. Let's see here. We have this website. VERTOGEN is a company that produces vertical axis wind turbines. This is in 5 blades, as we can see here. So as variable pitch vertical axis wind turbine, you can change the speed and accommodate the wind speed. So you can here check out this website to know more about that, and can find this. So here the blade pitch movement every RPM, they change the pitch. Okay, and we're gonna talk about the flapping airfoil, the same idea, and you can apply it on any vertical axis wind turbine. So we're gonna talk about that in details, but we're not gonna talk about the details of the geometry of this design because it is classified. We have already carried out the simulation for VERTOGEN company, and we got the results, and we compared the results against, or compared it to the fixed pitch vertical axis wind turbine, and the results, we're gonna talk about the results at the end of this video, but I'm not gonna share with you the details of the diameter and the dimensions and this kind of things. I'm gonna show you the idea, the general idea. Okay, so here we can see also, just wait please. So here when the turbine invader looks to generate investments, we have to check out if you are interested in contacting with this company to know more about it. And we're gonna see, so here, first of all, we have to talk about the different types of wind turbines, and also the theory of the airfoil, pressure side, pressure side airfoil, as you can see here, because there is velocity difference and pressure difference. Here is the suction side, longer length and fast moving air at low pressure, and here is slower moving air at higher pressure. So here the pressure side, shorter length. That's why the lift force is created, and also the drag force is created due to the viscosity of the fluid. The drag force is always in the direction of the flow, and perpendicular to it the lift force is created. Okay, so this is the simple, and here we have a lot of simulations. Also, we carried out many simulations on YouTube about this. We have in my playlist, you can check out my vertical axis wind turbine simulations. What's this? So this is, I'm going to show you here the lectures that I attended 4 years ago at college. It was generated by Dr. Aya Diab. Here, she is one of the doctors who works on the renewable energy research, and she's now, I think she is working on nuclear research, I think in South Korea. So let's see what we want here. just please. Wind turbine performance, of course, you know, here are the blade angles and here are the velocity diagrams. As you know, each turbine or each airfoil has a velocity diagram like this, especially with the wind turbine here, the reduced power coefficient, wind turbine performance, the power coefficient and the torque on the moment coefficient, the variable speed, and you can change the principal pitch control here. So we have here the constant speed fixed pitch. So here we have fixed speed, fixed pitch. So impossible to improve performance with active control. Only stall control at high wind speeds is possible. Okay, we reach to the angle of attack that causes stall to stop the turbine. So in this design, the turbine's generator is directly coupled to the power grid, causing the generator speed to lock to the power line frequency and fixed rotational speed. From the figure, it is apparent that the actual power does not match the ideal power. Of course, because the angle of attack does not change. Okay. So implying that there is low energy capture. Notice that the turbine operates at maximum efficiency only at wind speed in low speed region. The rated power of the turbine is achieved only at 1 wind speed as well. This implies poor power regulation as a result of constrained operations. This is the fixed speed fixed pitch. For fixed speed variable pitch, here operates at a fixed pitch angle below the rated wind speed and continuously adjusts the angle above the rated wind speed. Here both feather and stall pitch control methods can be used to limit power. Keep in mind that feathering takes a significant amount of control design and stalling increases unwanted thrust force as stall increases. So below the rated wind speed, the FSVP turbine has near optimum efficiency around region 2. Exceeding rated wind speed, the pitch angles are continuously changed, providing little to no loss in power. And we have here variable speed fixed pitch. We have the third type of wind turbines, continuously adjust the rotor speed relative to the wind speed through power electronics controlling the synchronous speed of the generator. So the generator is isolated from the grid so that it's free to rotate independently of the grid frequency. This is a very important point. Fixed pitch relies heavily on the blade design to limit power through passive stall. The power efficiency is maximized at low wind speeds, and you can achieve rated turbine power only at wind speed, at 1 wind speed. Okay? Why? Because this is a fixed pitch. Passive stall regulation plays a major role is not achieving the rated power and can be attributed to poor power regulation above the rated wind speed. In lower wind speed cases, VSFP can capture more energy and improve power quality. And of course, we have here the best choice, especially for the turbines that will generate lots of energy. So here, operating below the rated wind speed, variable speed, and fixed pitch are used to maximize energy capture and increase power quality. Okay, so see here is the variable speed and variable pitch. Okay, it's variable and variable. Bringing above the rated wind speed, fixed speed, and variable pitch permit efficient power regulation at the rated power. So here is VSVP is the only control strategy that theoretically achieves the ideal power curve. Again, operating below the rated wind speed, variable speed, and fixed pitch are used to maximize energy capture and increase the power quality. Operating above the rated wind speed, fixed pitch, and variable pitch permit efficient power regulation at the rated power. Okay, so we have here 4 kinda wind turbines, and we're gonna talk about the design of VERTOGEN in the next couple minutes through their website. Okay, but now we're gonna talk about, let's see, the aerodynamics. You can use this book for more information about the turbines and the airfoil and theoretical. And here's the lift, the angle of attack. Here is the lift force, and here is the drag force. And as you know, you can see here the vertical axis wind turbines. The torque is generated, or the moment is generated due to the force here, the tangent force, okay, multiplied by the distance or the radius of the rotor. Okay, that's why you can find this turbine rotating. Okay, so here for the CFD, or computational fluid dynamics, it's another story. You can use Ansys Fluent for this kind of simulations. I covered this kind of discussions or these kind of topics in my previous videos, so please, you have to watch them if you did not. And for the CFD course, you have to take a CFD course to know the fundamentals of the CFD simulations, and also you can check out this channel, and there are many channels that talk about CFD principles, full lectures, and they are very helpful, really. And also you can check out this website, and this is the doctor who created this website, is Dr. Ahmed El-Maki here, and you can find a lot of things, useful things here, or especially about coding, because we're gonna use the user-defined function for our simulations today. So let's get started. Now we have here the fixed domain. We just have here these dimensions, and we're gonna use sliding mesh technique, not the dynamic mesh. No need for the dynamic mesh. Dynamic mesh is not our target, because I want to show you the principle. Okay, just have patience, please. So here, sliding mesh modeling, the theory of the sliding mesh. Here in the moving zone and the stationary zone, and here we have interface between them. As you know, here the moving mesh equations. So what we want here, so here is the time step. You can use these kind of equations to know the time step, and recommended time step size is based on the principle that the time step should be no longer than the time it takes for a moving cell to advance past a stationary point. So an estimate for this time step can thus be calculated as this: delta t equal delta s by v moving. And here is the example flapping airfoil. This is the simulation that we're gonna carry out today. Here is oscillating inner zone and the stationary outer zone. Here is a stationary, and here is the rotating. Okay, so here is Mr. Mike folder. Use this. It's not for the dynamic mesh. I used this for a dynamic mesh, but here is flapping airfoil, sliding, stationary domain, step file, where Just click save. Okay, and here the it's a random airfoil, and of course, as you know, this diameter must be the same diameter of this. Okay, because this is gonna be the rotating domain. Just export. Yes. So now let's start in Ansys XY plane. Let's import external geometry file. Default domain. Okay. Because that will be a sliding mesh technique, so this is gonna be add material and line. Yes. Okay. Just we're gonna create surfaces from edges. Of course, this domain is random. Of course, you can only use your dimensions, generate, and then I think can make it from edges. I think it will be the same. Okay. No, I'm sorry. Surface from edges. Okay. Okay, it will give the same result. Surface from edges. I want a boolean. So now we have two surfaces. As you can see, this surface and this surface. Surface and this surface. Okay, we have two surfaces. As you know here, airfoil dynamic mesh. No. Okay, it's not a problem. Now remember that it's not a dynamic mesh. Just boolean. We're gonna subtract this target body, and here is this circle. Okay, now I'm gonna import the other domain, the rotating domain, add frozen, because this add material, it must be add frozen. Okay, if this add frozen, so this will be add material, but I recommend this. If both are add material, it will not work. So now we have here the domain. So to see it, just hide all other faces. Now we have here to suppress this body, just to see surfaces from edges. And also surface is from edges. I want to create boolean. Select the domain and the other. Click here. Be careful. Body, okay. So now I want to simulate the air past the airfoil. That's why I want to make it like this. Okay. That's why I use boolean. Now right click and unsuppress all bodies. If I do this, hide all other bodies, notice that you must not find anything here. Okay, this means that we have here fixed domain and we have the rotating domain. Two separate domains Okay, so now we have just finished the geometry. Please hit save to avoid any trouble, and you may not, or you may lose the data. Okay, just close. Just reset and open meshing. As you know, for meshing is very critical step. You have to know that you have to calculate the Y plus, of course, for the airfoil or the wind turbine you use. You can use this formula to get the first layer thickness. Okay, here is the first layer thickness. This airfoil, or in another meaning, the Y plus. How to calculate boundary layer thickness, very critical. It depends on the turbulence model you use. Y plus calculator for a flat plate, and we have here a special formula for wind turbines or the airfoil, so we can use it. So delta y, the first layer thickness, equal the L, the reference. I think that it is the chord, and here the Y plus, and here is root 80, and then multiplied by Reynolds number to the power negative 13 to divided by 14. You can, according to the Turbines model, you should know the range of the Y plus, and you can put it here, and then you can get delta Y. It's very simple. Here Y plus calculator, it's the compute wall spacing for CFD, and you will find a lot of websites. So we have here the geometry. As you know, I'm gonna use a random mesh right now just for this tutorial, and please, you have to check out the research papers that you can use and how to do the refinement, how to do these recommendations. And here is the inflation, because this is an unstructured mesh, and you should do an inflation for the structured mesh surrounds the airfoil Y to capture the boundary layer, especially when you use SST model or this accurate turbulence model that captures the separation of the point separation between the laminar flow and then transition and then becomes turbulent. Okay, so this is a mesh. Here is sizing. I'm gonna make it, of course, let's make it fine and then update it. Okay, of course, here you must see the statistics, number of nodes and elements, and the quality. Quality here is very critical, especially when you use Fluent or CFX. You must not exceed 0.89 skewness. So here we have 0.64, so it's pretty good. It will give you a convergence, but of course we need to make refinement. I will let you do these kind of things by yourself, but I'm just showing you here the methods we can make refinement for this, refinement, degree of refinement, and then update it. Of course, you will do some refinements until you reach the delta y you calculated. Okay, it is not your choice, it is not your decision, only decision. It's according to this formula only, like this. Okay, so of course you should do more refinements if you still do not reach the first layer thickness. This is the first layer thickness, by the way, that we talk about. Why? Because if you want to capture the boundary layer or a specific formula, physical phenomena, this distance from here to here must not exceed a specific limit. Okay, that's why you have to use the refinement. But anyway, we're gonna proceed now. Now it's the time of the boundary conditions. So insert, I'm sorry, just hit here. Okay, just add all other bodies. Notice that because we have this line is not a single, or it's multi-lines, so please use Control and C here. Control, I'm sorry, Control and select all of them. Here is the inlet, and this line is gonna be the outlet. And here is the trick, is interface 1. And then right click and show all bodies. Then face, hide all other bodies. This is interface 2. And here is the airfoil. Why we name the airfoil? For the performance curves, airfoil. Also, we have here to select this, and this is the rotating domain or the flapping domain, by the way. It's not rotating as usual, but it will be a flapping domain. And also we have here this domain, other bodies, this domain, fixed domain. Okay, show all our bodies. So we have here only inlet, outlet, interface 1, interface 2, airfoil, rotating domain, and the fixed domain. Okay, so that's it. And if you are simulating the wind turbine, the same procedure will follow, but I will show you some differences, but not in details. I'm not gonna show you the details of their turbine. I'm gonna show you the general setup only. So here is the update. So now the setup, of course, you have to make it double precision for high quality results, and you can make serial or parallels according to the number of cells. And here is number of threads. I only have 4 threads, and you have to know exactly your RAM and your specifications of CPU. So I have here maximum 4, so you can set 3 or 4, but I'm not gonna use it as serial because I'm not gonna run this simulation all the time. It's just for recording. I covered all of points, gentlemen, in my previous videos. That's why I'm not talk about everything in detail. You can watch my previous tutorials to be familiar with what I'm talking about, okay? Just have patience, and now we're gonna talk about the setup. Due to von Karman effect, it will be unsteady and transient, yes, and the models, so it's your choice for the model. You can use laminar, speller to almaras, k epsilon to equation, k omega, transition kkl omega, so transition SST model. This is the most common turbulence model that is used for high accurate simulations. As you can see here, SST k omega, also transition SST, where transition SST, transition k omega and k epsilon. So let's continue. When I use k epsilon realizable, so here realizable, I talked about that in my first 2D video and enhanced wall treatment, so please check out that video. So now we can complete here the materials. Be sure that the material here is air. Okay, if you wanna create, you can create another material if you use water. Now we have the cell zones. We have the fixed domain. It's a fluid, type fluid, not solid, and it's air. No further action, and here is the rotating domain. It's fluid, and here is the trick, air, and we're gonna use mesh motion for the sliding mesh, but we have to insert a user-defined function. Okay, so let's continue here. The airfoil, we have here the C code. That's why you should learn some coding. So we can here use this compiler. New, not Fortran, not yes, it's gonna be C++, and you can use it for the C codes. I copy and pasted this, but this is not what we want. No, so it's a flap C for UDF for specifying a time varying omega. Simulates plus minus 8-degree flapping with cycle of 1 second. Okay, so we have here include, and here the pi, and here define transient profile, speed, time, and we have real amplitude 2 pi multiplied by 15, and your real frequency and real omega. Okay, so we can save this, and I'm gonna leave some comments if you wanna simulate your turbine. Okay, we can hear. So this is flapping airfoil. Okay, dot C. Thanks. Okay, now let's continue. So go to user defined functions, enter predit, and you can get the user defined function manual online to know more examples about this. It's pretty amazing to use this kind of functions, and I showed how to use variable velocity inlet using a user defined function in one of my previous tutorials. We have here in the desktop. Please here. So this is flapping airfoil. Now interpret. If there is no errors, it will go smoothly. Okay, just close. Now, after that, this is pretty important. Mesh motion, okay. For the previous tutorials, I did not do anything here except that we defined the speed of rotation in radian per second, okay? But now it's not be a constant, it will be according to the UDF, okay? So just click OK. Now the inlet, suppose that of course I'm gonna use here 2 meters per second and the hydraulic diameter, and here is it may be 1% or 0.1 or 0.01 according to your real case. And the hydraulic diameter, you please use the chord length, so I'm gonna use one just to leave this as it is. And here according to your setup and of course according to your experiment, but it is zero gauge for the majority of simulations. And here please put it as you measured it or as it was recommended in the literature, okay? This affects the results pretty well. And here are the mesh interfaces. We have two interfaces, as you know, so we manual create, can make it interface or I. Interface 1, interface 2, and they create. That's it. Close. No dynamic mesh, and here the reference values are pretty important, gentlemen. The area I covered this information in the 3D simulation, the tutorial about the 3D simulation about the vertical axis wind turbine. So please, you have to check it again because I showed some recommendations from research articles on the Researchgate. You have to calculate the area and the depth and the length and these kind of things. Why? Because it affects the performance curves, as we will see here. Now for the methods also, you can use what you want according to the literature and according to the Fluent Theory Guide and the recommendations. Do not mess with these tabs or you will not get your results. I cover these kind of things, so let's move. And here is the monitors for the residuals. For high accuracy, you can increase the residuals like this, okay? And if you wanna make monitors for the drag and lift, can new force drag. You can, in this Ansys version, you can choose drag coefficient or drag force. Port file and plot and print to console. And here is the factor, okay. Just leave it. Okay. For definition, drag is not valid. Sorry. Force lift. Lift. I'm sorry, gentlemen, I forgot about edit. Yes, I did not use the airfoil, so that's why I used it. Okay, now is this the drag and new lift force, airfoil. For the turbine, you will use each airfoil. Okay. So then close. So we have files you'll find them in the directory of the project. And the initialization, and you can use this initialization and you will check out the conversions. That's pretty good. The activities are pretty important. The autosave, if you want to make an animation, you should eliminate this, maybe 10. If you make it 1000, it will be very hard to create an animation. I always use 10. Okay. Okay, I need solution animations. So select Move object if you wanna make the contours for pressure or velocity as you want, filled. For which domain you can make both, or you can make it for the rotating as you like. And click here, okay, and then you can run it. For the time step, as you know, you have to calculate it like what we have shown, and maybe open 001 here for this tutorial only, and please here you can put what you want here. Also, as if you make it 50, it will be more accurate for maximum iteration per time step. And you can save the project, because if any error happens, you may repeat the settings. Calculate. So as you see here, of course, if you use the recommended settings and values, you will find pretty well or better conversions. Here is due to the random settings and random geometry, and we have here the drag and the lift. And also there is an important thing, you can validate it to know exactly the reference area and the reference length values. You can go to NASA, for example 0012. If you use this airfoil, you can get Reynolds number and hold on please. Here are the contours, and here is the drag. So we have here lift coefficient versus alpha. According to your angle of attack, if suppose that it is a fixed angle of attack, you should know alpha or the lift coefficient at a specific alpha. Okay, that's why you can use this curve or this plot for the reference values. You can change the reference values and check here the values of the drag and the lift. Once you get the average right, okay, so you can continue using the reference values. This is the first thing you can do, and then you can carry out a lot of simulations based on these reference values, okay? And that's it. So I have here the simulations, no problem with it. And you can see here is this, as you know, it has just moved. Why? Because this is not the original position. The original position was 0 angle of attack. Now it dropped, as you see. So to save time, this is gonna be here and then become 0 again, and then become higher or give you the positive angle of attack. So just stop the iteration, and I'm gonna show you now how the simulation will be. So we have here the velocity, contours of velocity, as you can see. Velocity magnitudes. okay, and then it becomes 0 again, angle of attack, and then comes higher. As you see, it's pretty amazing to reach this. Okay, so also you can find another here, another simulation. So notice, so everything what you want here. Okay, so gentlemen, here is the simulation about flapping airfoil. Of course, you can change this using the flapping here. Okay, yeah, you can change the amplitude or the frequency and to change the omega. Okay, also you can use here an angle of attack not 0. You can make it as you want, and you can change these values to just make the flap angle you want. Okay, so it's here is the trick. This affects the angle, and also you can put here the maximum angle or the optimum angle as you want. So now, gentlemen, for the wind turbine, suppose that you want to simulate the wind turbine. So create new. Let's create sketch. So here, suppose that this is the rotor rotating domain, and as you saw, here is the airfoil. Suppose that you wanna create the turbine. Just copy it here. Let's make it millimeters. Okay. And this is the circle. Also, this not gonna be okay. Just move it. Move it here. And here is the rotor. Okay. And this is the airfoil with this circle, and just to make it circular pattern, and it will be 3 blades. Okay, as you can see here, so this is the airfoil and the other airfoils. So why do we do this? The only difference from this design and the fixed pitch, that the fixed pitch we do not use as you know, these circles. This is gonna be the rotating domain, the inside flapping domain. So this is the rotating domain, and this is the flapping domain number 1, and flapping domain 2, and flapping domain 3. For each domain, we will use a UDF function if you want, as you want to set the data of the angles. As you know, we can see here for flapping airfoil, you can make many UDF functions in a separate in this single. So suppose that this is one yield 1, and here is 1, and speed 1, time 1, and omega 1, 1, frequency 1, time 1, 1. Okay, so you can just copy this, and I'm sorry, paste. No. Copy and paste. We have here 2, 2, 2, 2, 2. Control V, copy, 3 for the 3 airfoils, another 3, another 3, 3. Okay, you can change any values of this 1, 2, 3. Okay, save it, and so let's see here. For then, and you then after that you can save the sketch, and you can export it as you know. Okay, and this diameter must be as this diameter. Okay, so after that you can import it in Ansys. So open here Ansys and import external geometry, and we have here this new add material. Yes, okay, the same way from edges. Lean, yes, yes. So now we have here this, and the port is port 1. At frozen, yes. So now we have here this, and suppress concept surfaces, I want to make surfaces booleans from this. Yes, this is the first thing. Or, I'm sorry, we have here to make something before that. When you your surface from edges. Okay. This part is tricky. Okay, we have here that, and then edges. Okay, and boolean this from this. Okay, now we have that. Okay, after that you can make a surface. You can make this again, and surface again, and boolean this from that, from the airfoil itself. So here is the trick. Can make this. So as you know, 1, 2, this is what I want. That's exactly what we did last couple minutes. So again, surface from edges. This generate the boolean, the rotor, rotating domain from the flapping. This is the flapping. Generate. Then concept, edges. Again, we're gonna make it surface. Again, the airfoil. Then boolean. Boolean this from what? From the airfoil itself. Amazing. It's pretty well. Concept, surface. The surface, then boolean from the rotor, and this. After that, I make surface again, and the surface again for the airfoil, and generate, create, boolean, no, here, and then the airfoil itself. Okay, now it is fantastic. Unsuppressible bodies. So we have here, gentlemen, the trick is that we have here, you have to save it to avoid any problems. So we have here the fixed domain and the rotating domain and 3 flapping domains. So now we have here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, just close it. So here is the mesh. So just generate mesh. Like I said, it's gonna be a random mesh. I have to calculate the y plus and apply it to each airfoil. Okay. The sizing for this tutorial, make it fine, and please check the skewness. Okay. Okay, and here is a refinement. Can make some refinements for this. Update. And here we go. And of course, you can have to make suitable sizes also for the fixed domain, not just refinement for the areas around the airfoil. No, because this will affect the solution. If these sizes are not suitable for these sizes and these sizes, the solution will not be accurate. Okay. Right now, just the same. And here is other bodies, fixed domain, okay, inlet and outlet, inlet, outlet, interface 1, okay, fixed domain, inlet, outlet, interface 1, show all bodies, and now add all other bodies. This is leading domain 1 or leading domain. We have here interface 3, interface 4, interface 5, okay, and then show all bodies. And now this is hide all other bodies. This is gonna be flapping domain 1, okay, and here we have 2. This is interface 3 2, okay, and the airfoil 1. That's it. The same way with the whole other airfoils. There's a piece of work with these kind of turbines. Okay, this is the face. We have here flapping domain 2, interface for 2, and here for 2. Thanks. And here the last thing are all of the bodies. Flapping domain 3, interface for just to have I think this is, sorry, 4 is 5. It's the phase 5 too. Okay, and therefore 3 air foil 3. Vielen Dank. So gentlemen, now we have here this mixer. Okay, so we have here fixed domain, inlet, outlet, interface 1, rotating domain, interface 3. Where is interface 2? Interface 2, interface, no. Here is rotating domain, okay. Just, there's something not right, I think. That's all other bodies, okay. Interface 1, interface 2, no, this is not interface 2. Yes, this is interface 2. This is what I missed. Phase 2, okay, and interface 3 and interface 5, okay, and here is interface 4, okay, that's it. And then show all bodies, and then here is 3 2 with 3, okay, and 4 2 with 4, okay, and 5 2 with interface 5. Where's interface 5? Here, yes. And therefore in the interface 1, this is with interface 2, yes. So now this is right, okay. Again please. So inlet, outlet, interface 1 with interface 2, yes. Interface 3, where? This. So where is 3 2? 3 2 is this. And interface 4, this with 4 2, yes, and 5 2 with 5. Amazing. And airfoil 3, airfoil 2, airfoil 1. Vielen Dank. Just update it. So after gentlemen finishing, we have here transient and the models. As you know, it is up to your research, okay. And then the material, it's gonna be air by default. So we have here gentlemen fixed domain and okay, here no problem, and rotating domain, and here mesh motion. Okay, we have here, according to this design, is 3049. Okay, but this is the rotating domain diameter, okay. So you have to know the dimension of your rotor according to your rotor diameter, the rotor itself. This. So this is the rotor. The turbine rotor is from here to here. This is the rotating domain, okay. So according to the experimental setup, the velocity divided by the radius of the rotor of the turbine itself gives you the rotating speed. So according to that, you can just measure it. It's gonna be 1 0. Okay, suppose that you have 14 meter per second wind speed. Of course, it's a very high speed divided by 1074 because it is a random in meter at 1 meter 0.074. So it will be 13 radian per second. Okay, so it's gonna be 13 4. Okay, 13 radian per second. Velocity divided by the rotor, 15 radian per second. Okay, no problem in this, but here is the trick. Flapping airfoil number 1. Flapping airfoil number 1, we have to use the user-defined function. Interpreted, browse. We have here is the flapping airfoil. We edited this for the 3 airfoils. Okay. On desktop here, if there is an error, you will notice this. So no problem. Okay, and here are the mesh motion, and it's not gonna be absolute, it's gonna be to the rotating domain. Okay, and here the rotation axis is pretty important. Why? Because the rotation axis is here. Where is this point? This point, it is x0 and 1074.738. 1074. Okay, we may make it in meter, will be easier. Yes. Again. Okay, minus 0, of course, 0, 1.075. 0, 0.74, I think. Here, 5. Okay. So, gentlemen, here is the code for the 3 airfoils. You can change what you want, of course, and we have here interpret it again. Okay, no errors. So cancel this, open it again. Mesh motion, this flapping airfoil air. Okay, and here is the rotating domain, and here is 1.075. I'm sorry, 0. 1.075. And it's not gonna be constant. No, it's gonna be for airfoil 1. Amazing. The same here. Go to Inventor. This point. Minus 0.931. Okay. For Y, minus 0.537. And B. Thanks. Motion here for the rotating. And here is the last thing. 0.931 positive, 9 negative. Okay. 131 and negative 537. negative 537. Okay, again 537. Has no constant, it's gonna be C. All right, and here is the rotating domain as we know, and that's it. For the boundary conditions, suppose that 14. And of course I will let you choose these kind of things. For the hydraulic diameter is the chord without pressure 0, and you have to check on this. Okay, the mesh interfaces you have to make it interface 1 I1 between I and 2, create phase 2 between 3 and 3.2, 3, 4 and 4.2, 5, 5, 5 and 5.2, and that's it. 5 interfaces close. That's it. No dynamic mesh and reference values. Please check on the video that I talked about these kind of things, and you have to do trial and error simulations until you get the right performance compared to the experimental results, of course. And here are the methods, and I will let you do it on the controls. And here is the monitor, and as you know, here are the residuals. I'm not gonna repeat myself. Here import files. You can do as we have just seen, the drag and the lift for each airfoil. Okay, but we're gonna here the new thing is that I'm gonna show you how to get the torque of the turbine for airfoil 1 and 2 and 3. This the whole turbine. Okay, and here moment center 0, 0, moment x 0, 0, 1. Okay, and report file. Okay, so this is the new thing here, and that's it. And here the initialization, as you know. So let's see the conversions. Wow, it's pretty amazing. It's considered to be conversions if it is 10 to the power -4. The activities, the solution animation, as you know. I'm sorry here, and you have to make the autosave 10. Velocity here is for the whole internal, like that. Okay, and choose it. Okay, and the time step, you can use this formula or this method. Here is the RPM is 150 revolution per minute. It means 2.5 revolution per second. Here, yes, that's right. This means that the turbine, if you multiply this by 360, it will be 900 per second. So 100 will take this. So it was the first attempt for these researchers to use this delta t, but they did not get the conversions, so they tried to another time step. As you know, you have to carry out some simulations as initialization for a first attempt, and then you can get the conversions you want. You can make it here 50, and then here. Okay, as I expected, you you got an error. So you have to reopen it. This error is due to using Ansys heavily. Just reopen it. So do not panic, and I hope we do not repeat the same things. We're gonna find out. That's why I always tell you you should save your work. Okay, let's see. Okay, no need to do anything. We have everything here is here. Okay, so just hit calculate. Yes, initialize again. And here is the contours. Of course, we did not do this. And here is the moment coefficient. Of course, we are using a very random reference values. So the moment coefficient, I'm not sure about it at all. So you have to validate this coefficient. This is the moment coefficient. Okay, not the moment in Newton multiplied by meter. Okay. So here is the turbine. You can be sure about this moment from I think reports, and then you can get the moment at the time step you are at. So here is the turbine. It has just rotated. Yes, as you can see, the flapping domains are rotating with the rotor because we used the coordinates of each point. If you do not do this, you will not find this shape. You will find that the rotor is rotating by itself and without taking the other flapping domains with him with it. Sorry. As you can see, now it's perfect. This is a vertical X wind turbine with a variable pitch. You will find this pitch. Notice that this has just moved, and now it's a zero angle now, and it will now notice that the angle of attack increases. It's pretty amazing. Notice now it is positive angle of attack. The same is applied on the other airfoils. If the user defined is the same, of course you can change what you want for each airfoil, and this is the magic of coding. You can control everything from here. So this is the idea of the flapping airfoil, and here you can check out the data. Now it is 0. So what if you change the velocity or the rotating speed? Here is 13. What if it is half of 13? What if it is 6.5 and I don't want to change anything and I want to run another simulation? Just you go here and change the frequency. So 6.5 divided by 13, it will give you half. 1 by half is 2. So 2 is multiplied by this frequency, it will be 4. This if you changes the rotating speed. If you divide, if you are 13 and you wanna be 6.5, you have to make the frequency like this. And of course, if this frequency is 4 from the beginning, it will be 8. And if this half, it will be of course 1. Okay, so this is the idea of changing the frequency by changing the rotation speed. Okay, why? To just keep the angle of attack as it is, or the maximum and the minimum angle of attack plus minus. If this is designed to be plus minus 8, just change the frequency. Why? Because the time domain will not be the same. Thank you very much, gentlemen. This is the tutorial. I'm sorry you have a tough tutorial, and I hope this helps you. So let's get back to the turbine of VERTOGEN. So the turbine of VERTOGEN, we have carried out a lot of simulations from at many rotating speed, and I'm sorry I am not authorized to share with you the details of the geometry and this kind of things, but I got the permission from Mr. Mike Chung here, who supported me with the data to run his model. He supported me with the values of the angles and the airfoil, NASA airfoil that he uses for his actual turbine. So I only can share with you the animation that we got and the comparison between the fixed pitch and the variable pitch they have. So please hold on. So we have here a fixed pitch variable speed vertical axis wind turbine and a variable pitch variable speed vertical axis wind turbine at wind speed 14. So let's see. Okay, here is the wind direction. This is the fixed pitch. Okay, as you can see, here is the velocity contours, and the pitch does not change. It's all the time. So this is not good, and you cannot optimize the wind or the power. Why? Because it is only at a specific wind speed. You have a Reynolds number, and this Reynolds number you can at a specific angle of attack, and Reynolds number you can capture the power, and it's not all the time. Okay, again, this is fixed. Now here is the variable pitch. As you can see, we have here the domains, and at each location the variable pitch is changed, and this optimizes the power extraction. Why? Because the variable pitch lets the flow here, and the flow domain is changed around the airfoil, and this of course changes the performance. So the airfoils have variable angle of attacks, many variable attacks. Okay, Thank you. And here, the final thing that I want to share is the torque at 5 meter per second. I asked Mr. Mike to show this, and he agreed. So if you compare his turbine with the fixed pitch turbine, you'll find here that his turbine gives you a higher moment or higher torque, and of course this shows that you can get higher power coefficient and power in kilowatts. Okay, as you can see, the variable pitch is higher. We did a lot of simulations, and all the simulations showed that the variable pitch gives you moment coefficient higher than the fixed pitch. Okay, and here's the lift coefficient of a specific airfoil. As you can see, the lift coefficient of the variable pitch is higher at the majority of the time, and we calculated the average, and it was higher than the fixed pitch. And here the drag coefficient, the fixed pitch has a drag coefficient more than the variable pitch. So as you can see, and also it was calculated using the average criteria. So we have here a higher lift for the variable pitch and lower drag for the variable pitch. So this means that that's why the torque here is higher than the fixed pitch. Thank you very much, gentlemen. Please, I'm gonna leave the email of Mr. Mike Chung under this in the description of this video, and the website of VERTOGEN if you are interested in to know more information about his design, and if you wanna ask him any technical question related to his real design, please contact directly with him. If you want to ask me about any technical information related to the CFD about this vertical axle wind turbine, please go ahead, as you know. But as you know, please do not ask me about any data or classified data related to this turbine. Okay, thank you very much. I'm sorry this tutorial is so long, but I wish you are happy right now. Thank you very much.